Dear students, welcome to the EPG Pathshala. I am Dr. Gurmeet Singh, working as a professor in the chemistry department of University of Delhi. Today, we are going to discuss about a very important technique called Kelvin probe force microscopy. And this module will discuss the instrumentation involved in this particular technique. This also comes under the paper Surface Analytical Technique Part 1. After completing this module, you will be able to understand very completely the introduction and working part of this and preparation of atomically sharp and conducting AFM tips, which is extremely useful in any of the surface analytical systems. KPFM is primarily based on the instrumentation of an AFM system. That means the basic principle remains similar in both these. AFM operates in contact, intermediate, which we call it as tapping mode, and non-contact modes. In contact mode operation, the AFM tip touches the sample surface and the tip sample repulsive force deflects the tip cantilever. The cantilever deflection is monitored and is used as a feedback signal to know the extent. In intermediate and non-contact mode, the cantilever is externally oscillated at or close to its resonance frequency. The tip sample interaction is altered as the tip sample distance changes, leading to a change in oscillation amplitude, that is what is called intermediate mode, and resonance frequency, where it is non-contact mode, which is used for this technique. These amplitude and frequency changes, which we find here in a variety of modes that we operate this system in, with respect to the reference amplitude and frequency, they are both used as a feedback signals to obtain the topography of the sample surface. Therefore, intermediate mode and non-contact mode are referred as amplitude modulation, which is abbreviated as AM, and the other is frequency modulation, which is FM operation, respectively. In intermediate and non-contact mode, AFM, when we operate, the tip sample interaction is perturbed by attractive and repulsive forces, causing amplitude or frequency changes in the oscillation of the AFM tip. In AM mode, that is the amplitude modulated one, AFM changes in the oscillation amplitude provide the feedback signal for the imaging, which is analyzed further. The amplitude of oscillation increases as the tip sample distance increases. This is an important condition, that as the amplitude of oscillation increases, the tip sample difference distance also increases. This happens due to the decrease of the tip sample interaction. The amplitude change is monitored and regulated by a feedback system to keep the tip sample distance constant at a predetermined set point. The dependence of amplitude change on the tip sample interaction can be described analytically based on the harmonic oscillator model, and the amplitude change is generally accepted to be dependent on the force between the tip and the sample. Therefore, AM mode measurements represent the direct force between the tip and the sample. In FM mode AFM, changes in the oscillation frequency provides information about the tip sample interactions. The cantilever oscillation frequency Changes due to the tip sample distance variation. A feedback system regulates the frequency change to keep the set point frequency constant, allowing the topography of the sample surface to be acquired. The changes in the oscillation frequency are dependent on the force gradient between tip and the sample when restoring force of the cantilever that is associated with the tip oscillation energy is large compared to the interaction force between the tip and the sample surface. Therefore, the FM mode in AFM detects the force gradient rather than act as the force itself. A factor enabling AFM mode AFM, a factor enabling FM mode AFM to have higher spatial resolution than AM mode AFM. We'll soon show you the schematic diagram of Kelvin force modulated microscopy, or Kelvin probe force microscopy as we have been calling it. The experiment apparatus which is used is shown in the next slide. The lower part of the frequency modulated mode AFM system for topography measurements, and the upper part shows the components for CPD mapping, including the KPFM controller and the lock-in amplifier which is used when we operate this. In this slide, the dashed line and the bold straight line in the diagram show the AM and FM mode KPFM configurations, which are both very important when operating this. Vacuum is applied to the tip from the lock-in amplifier, and reference signal voltage output is given, which is abbreviated as OSC, outgoing voltage. In frequency modulated mode, the frequency shift signal F is split into two parts. One goes to the Z regulator, which is primarily for topographic imaging, and the other is fed into the lock-in amplifier. This lock-in amplifier obviously extracts the signal and then same frequency as vacuum, and feeds the signal into KPFM controller. The KPFM controller maintains feedback to nullify the lock-in output signal by applying VDC at the tip. In AM mode, potential at alternating current, that is VAC, with same frequency as the second resonant peak of tip oscillation is applied to the AFM tip to excite the tip with electrical force. The amplitude of the tip oscillation has two components: low frequency, the first resonance peak, tuned by mechanical oscillations, and high frequency. The second resonance peak is tuned by the potential at alternating current. A band pass filter filters the low and high frequency signals. The low frequency signal is used for topography regulation. The high frequency signal feeds directly into the lock-in amplifier. The KPFM controller measures CPD using the second resonance component. This slide talks about KFM, Kelvin probe force microscopy, instrumentation, and preparation of conducting AFM tip. This measurement will be possible if KPFM instrumentation is properly carried out. The lower part of the diagram that was shown in slide talks about FM mode, APFM, and the one which is used for topographic measurement, and the upper part shows components for CPD mapping. Both can be carried out with the help of this particular force microscopy. The KPFM controller maintains feedback to nullify the lock-in output signal by applying potential at direct current, potential DC, to the tip. And in AM mode, potential in alternating current with the same frequency as the second resonant peak of tip oscillation is applied to the AFM tip to excite the tip with electrical force. The amplitude of the tip oscillation has two components: low frequency, the first resonance peak, tuned by mechanical oscillation, and high frequency peak, the second resonance peak, tuned by potential at alternating current. A band pass filter filters the low and high frequency signals. The preparation of atomically sharp and conducting AFM tip is critical for high resolution KPFM equipment. An AFM tip can be prepared for high resolution KPFM measurements using any of these several methods. The most common method is to take a commercially available heavily doped silicon cantilever and use heat treatment followed by argon ion bombardment to remove the native oxide layer and other contaminants. The tips routinely produce high resolution images but are more likely to pick up surface atoms, altering the work function of the tip. The other method is some commercially available tips, for example, platinum iridium coated silicon cantilever, can produce sub-nanometer resolution of KPFM images. The commercial platinum iridium coated tips do not require substantial tip preparation, but yield low specific or spatial resolution. We can also use HF wet etching of silicon tip followed by a high temperature annealing has also been successful for high resolution KPFM images. Comparison of KPFM to other surface potential measurement systems can be very conveniently carried out. The surface potential or work function of a sample can also be measured by various techniques such as Kelvin probe, photoelectron spectroscopy, in short it is called PES, and scanning electron microscopy SEM with electron beam induced current EBMIC analysis. Similar to KPFM, the KP also measures the CPD between the probe and the sample surface. The working principle of KPFM and the KP are similar, but KP is an averaging method including the CPD values of the other sample area, which does not provide a map of the CPD on the sample surface. P measures the energy of photo-stimulated electron emitted from a sample surface. Angle-resolved high-resolution PES can be used to determine the electronic band structure of the sample. SEM can also resolve the local electronic structure of the semiconductor sample by measuring EBIC. Gives the flow chart diagram of Kelvin probe force microscopy. It indicates very clearly what way this particular force microscopy works, and this schematic diagram of KPFM experimental apparatus has been very clearly given in this slide.
The KPFM experimental is an AFM based apparatus. The basic operational principle and instrumentation of AFM and KPFM are reviewed together. A comparison is made between KPFM and other surface potential or work function measurement tool. Recent reports show the KPFM can be used to image potential distributions on the surface with sub-nanometer resolution, making KPFM the best technique at present for characterization the electrical properties of nanostructures. KPFM measures a contact potential difference (CPD) between the sample surface and the tip. In high resolution KPFM, CPD is strongly affected by the short range force between tip and sample. The CPD associated with the short range force is specifically referred as the local contact potential difference (LCPD). For the high resolution KPFM, understanding the fundamental difference between the CPD and LCPD is critical, as is knowing how the CPD and LCPD correspond to physical properties of the surface. Application of KPFM to electrical property analysis of nanostructure are reviewed in the second part. KPFM characterization of the electrical property of metallic nanostructure is described. KPFM has enabled the experimental determination of quantum size effect on the electronic property of metallic nanostructure. Point 2. KPFM has been used to study the electronic property of semiconductor nanostructures and surface. Electronic property of defect on clean semiconductor surface have been investigated using sub-nanometer resolution KPFM. High resolution KPFM has been successfully applied to the study of a variety of adsorbate and their interaction with semiconductor surface. Point 3. High resolution KPFM has been used to probe semiconductor device. A notable application of KPFM is the imaging of operational electrical devices to provide the high resolution potential profile. These measurements provide critical near atomic scale information on the processing induced defect and their effect to the performance of the electrical device. Basic principle of atomic force microscopy. KPFM is primarily based on the instrumentation of an AFM system. AFM operates in contact, intermediate, tapping, or non-contact modes. In contact mode operation, the AFM tip touches the sample surface and the tip sample repulsive force deflect the tip cantilever. The cantilever deflection is monitored and used as a feedback signal. In intermediate, the non-contact mode, the cantilever is externally oscillated at or close to its resonance frequency. The tip sample interaction is altered as the tip sample distance changes, leading to a changes in oscillation amplitude, intermediate mode, and resonance frequency, non-contact mode. These amplitude and frequency changes with respect to the reference amplitude and frequency are used as feedback signal to obtain the topography of the sample surface. Therefore, intermediate mode and non-contact mode are referred as amplitude modulation and frequency modulation operation respectively.
When semiconductor sample surfaces are bombarded by energetic electrons, they typically have several kiloelectron volts energy. Electron-hole pair are generated. The generated electrons and holes are free to move in a sample. In the absence of any local electrical field, these electrons and holes move randomly and typically recombine. When local electric field exists within a semiconductor sample, the local electric fields can separate the electrons, the holes, and the EBIC can flow throughout the sample. The EBIC is linearly dependent on the local electrical field. on the sample surface. The surface potential of a sample as a function of the local electric field is mapped by measuring the EBIC signal during the scanning of the electron beam over the sample surface. The spatial resolution of Kelvin probe force microscopy is higher than the PES and EBIC methods. The sensitivity of KPFM in measuring either the surface potential or work function is comparable to PES for less than Kp. Typically, laboratory scale PES has been used to measure the electric band structure of the whole sample surface. The spatial resolution has moved gradually to 3 micron meter due to improvement in the plane source and electron energy analyzer. When synchrotron radiation sources are used for PES, a spatial resolution better than 100 nanometers is possible. The spatial resolution of EBIC technique can be 70 nanometers thick. However, the EBIC technique has some disadvantages in measuring the surface potential of samples. The technique can only be applied to a semiconductor sample since EBIC measures the current generated from the electron-hole pair. In addition, the absolute surface potential is difficult to quantify since the correlation between EBIC and surface potential values is not physically defined. Although KPFM has superior spatial resolution with relatively high energy sensitivity compared to the other measurement techniques, KPFM has some disadvantages too in measuring the absolute surface potential or work function of a sample. First, the absolute measurement of surface potential using KPFM requires measurement of the work function of the probe. This requires the calibration of KPFM probe on a sample with a well-defined work function. Therefore, two measurements are needed, one on the reference surface and the other one on the sample. The necessary exchange of two samples under the KPFM probe decreases the accuracy of the measurement. PES and SEM do not require calibration of the probe, and measuring the surface potential or capacitance of a sample surface becomes easier. The preparation of atomically sharp and conducting AFM tips is critical for high-resolution KPFM. An AFM tip can be prepared for high-resolution KPFM using any of these several methods. This you will find is done when the most common method is to take a commercially available heavily doped silicon cantilever and use heat treatment followed by argon ion bombardment to remove the native oxide layer and other contaminants from the surface, which makes the measurements rather easier. These tips routinely produce high-resolution images, but are more likely to pick up surface atoms, altering the work function of the tip. Therefore, this is important that we keep it similar. Second part of this, which has been written as B here, some commercially available tips, for example, platinum iridium coated silicon cantilevers, though they are expensive, can produce sub-nanometer resolution of KPFM images. The commercial platinum iridium coated tip do not require substantial tip preparation, but that shall yield low spatial resolution. C part of this would deal with hydrogen fluoride wet etching of silicon tips, followed by high temperature annealing, which has also been successful for high resolution KPFM imaging. Etching silicon tips is an alternative method to ion bombardment to remove the native oxide. The coating of silicon cantilevers with a very thin gold or chromium layer, typically a few millimeters thick, also produces high resolution KPFM images. Chromium coated tips are less reactive so that they have a more stable tip work function. Obtaining the best spatial resolution requires optimization of the tip coating film thickness. UHV field emission tip cracking can produce sub-nanometer resolution. A tungsten filament is positioned close to the cantilever and a high voltage is applied between tungsten filament and the AFM tip. Electrons tunneling from the filament to the tip remove the native oxide. The simplest method to make a conducting silicon AFM tip is gently touching the AFM tip, this tip end, into the sample surface, removing the native oxide.
KPFM shows an interesting advantages in the study of smaller devices. Surface impact devices perform better at smaller scale, and KPFM is very sensitive to surface properties. KPFM becomes an ideal tool to probe nanostructure for electronic properties. In this respect, KPFM performed in UHV can provide an advantage over in air KPFM because UHV avoids contaminants that may perturb the potential profiles. KPFM can provide critical information about surface potential distributions, which can help increase solar cells efficiency and device performance due to the versatility of KPFM to characterize electrical or electronic properties of surface and working devices. We believe KPFM will be showed by variety of scientific researcher in the future. However, the fundamental physics, specifically electrostatic interaction between tip and sample on the atomic scale, needed to be further elucidated for broader application of atomic resolution KPFM.
So, students, having given you the complete introduction of this particular important technique called Kelvin probe force microscopy, which, as I said in the beginning, is very similar to atomic force microscopy, which is written as AFM, is a very useful, powerful technique for probing electrical and transport phenomenon at the solid gas interface. In AFM, when we utilize two types. One is a contact mode and the other is non-contact mode. And here we have a similar kind, is the contact one and the other is non-contact one. But here we call them frequency modulated and the other modulated AM modulated type of microscopy. Now the extension of KPFM capabilities to probe electrostatic and electrochemical phenomenon at the solid-liquid interface is of interest for a broad range of applications. When I say broad range, that means from energy storage to biological systems. And not only that, when we say energy storage systems, this shall also include lot many electrochemical reactions which will take place when we talk about phenomena like corrosion, or various types of corrosion which are taking place at the surfaces, their protective methods, their inhibition mechanisms, or a very dangerous form called pitting corrosion, or energy storage material, or the other important surfaces or surface techniques called catalysis. All these would very effectively utilize this in terms of solid liquid interfaces, which are of a great interest to the researchers. Continuing with the summary of this particular KPFM technique, we find, however, that the operation of KFM implicitly relies on the presence of a linear lossless dielectric in the probe sample gap, a condition which is violated for ionically active liquids. Therefore, this cannot be used in such a condition. And that example is when diffuse charge dynamics are present, then we cannot very effectively measure this diffused situations. I hope this would have clarified the Kelvin probe force microscopy, which is a very recent technique, has not been put into very many areas, but then looking at the fineness of this, it is certainly going to be a very powerful potential technique in the future to come. Thank you very much, please.